Myself, Dr. R. Avudeyamal, Professor, Department of ECE, St. Joseph's College of Engineering, here to present the topic Introduction to Multimedia Compression. What is multimedia? See, multimedia is a combination of text, images, audio, and video. The combination of these four or the combination of text and images and altogether. So, when these informations are to be transmitted in the digital form, the source is generating this data, generating this information or to be converted into a digital form. So, the information source for the text is a keyboard, and for an images it is a camera, and for an audio it is a mic, and for video both camera and mic together. So, when it is on keyboard, this text information consists of our alphanumeric characters, or special characters. When we are considering an images, this camera can be an analog camera or digital. What is meant by this analog camera? In the previous days, in the olden days, the images are being captured using in the film, and that will be taken as photographs. Nowadays, we want everything in the digital form. Therefore, the hard copy of the photo can be converted into the digital form by doing the scanning or by doing the bitmap form conversion. Whereas in the digital camera, while storing the image itself, it is stored in the digital form, that is in the two-dimensional matrix form. And when you are considering an audio, the mic is an information source, and the type of information can be either our speech signal or the music signal. Based on the frequency, we are categorizing this into speech and music. And this video, it is a combination of our images and audio information. Next, we are going to see the compression. What is the need for compression? As I told, when the information are being transmitted through the channel, it consumes the bandwidth of the channel. When it consumes more space in the memory, in the storing devices, automatically it consumes more bandwidth. So, nowadays the bandwidth is a very, very important resources in the digital communication system. Hence, we are going for compression. What is compression? It is the process of reducing the volume of information to be transmitted or reducing the volume of information to be stored, or else reducing the volume of information to be transmitted, that in the sense the bandwidth occupancy will be lesser. So, the compression is the process of reducing the volume of information to be transmitted. So, when you are reducing the volume of information, on what principle you will reduce the volume of information? Whether you will lose some data or you will simply ignore some data, based on that, the compression is categorized into two types. The first one is an lossless compression. Second one is lossy compression. Based on the principle behind the compression algorithm, it has been categorized. Okay. So what is multimedia data? As I told you, text, images, audio and video. So for what type of information we can go for lossless compression? For the text, definitely we have to follow a lossless compression, because when this text information is being stored in the memory of our system, conventionally it is follow our ASCII coding, that is American Standard Code for Information Interchange. It is a 7-bit code. For example, if I am transmitting the data aid, the alphanumeric character of A is 64. If I am taking the ASCII code of A is 64, and due to the error or due to the loss of information, if the value of 64 is modified to B, the complete meaning is changed. The 8 has become bid. The total meaning is different. Therefore, definitely for lossless, we have to use our text compression. For the text, this lossless compression is preferred. And lossy compression. For an images and a video, the lossiness is acceptable. For example, the image of a tree is being transmitted. The portion of a tree is clipped or lost by some shaded information. By the human intelligence, we can identify that it is a tree. Therefore, it is a basic example. So, likewise, this lossiness is acceptable for an images and video. But it is not true always. For an entertainment applications like this is acceptable. But when we are going for a medical diagnosis using an images, by that time definitely we have to follow our lossless compression technique. So, based on the applications only, we can use the lossless or lossy. Now, we will see what is lossless compression. We know compression is the process of reducing the volume of information to be transmitted. So, who will do this lossless compression algorithm? Who will perform this lossless compression algorithm? Because we have an information source, the output of the information source will be given to a source encoder. The source encoder is responsible. Some algorithm in the software or hardware can run on the source encoder to do this compression algorithm, whether it is a lossless or lossy. So, source encoder is going to perform this lossless or lossy compression. So, it is a schematic for this. Okay. Now, the lossless compression in the sense, the output of the decompression algorithm and the output of the information source should be an exact replica. That is, it is in the reversible form. We have a source encoder. The encoder is going to perform the compression, and this compressed information is transmitted through the channel, and then at the receiver side you will have a decoder, and that is going to perform our decompression, and we will be playing out at the destination. So, we have an source encoder, the output is going to a channel, then from the channel it is coming to a decoder and the destination. So, in the lossless compression, if I am considering this is X and this is Y and this is my input X2, it is an X1 and it is coming here X3, and I am considering this is my Y1 and this is my Y2. When this X1 is equivalent to Y1, I will name it as a lossless compression, exact replica. That is the output of the source and the output of the decompression algorithm, both are exact replica. That is known as a lossless compression. Lossy means it is not reversible. Some information will be lost. Now we will focus on this lossless compression techniques. As I mentioned, it is specifically used for our text. For the text, we are going to use our lossless compression. In this, we have two types. One is referred as an entropy encoding, and another one is source encoding. Under the entropy encoding, we have run length coding and statistical coding. These are the methods we have to do this compression. Okay, first we'll see what is meant by entropy encoding. Entropy encoding is based on the representation of information we are going to perform the compression, not based on the type of information, based on the representation of the information. So, encoding is based on the representation of information. Based on the representation of the information, it is being carried out. Now, first we are going to see what is our run length coding. Run length coding is mainly used for compressing our digitized documents. How we will digitize the documents? The document will be passed through the scanner, and the scanner will be producing an output of ones and zeros. So, when you have the long string of zeros and ones, this run length coding is used. So, as I told you, this entropy encoding is based on the representation of information. That representation consists of long string of ones and zeros. Then we can go for our run length coding. I will give an example for this run length coding. Assume that you have a digitized document. It is on white sheet and I have only one dot in it. So, it has a continuous white pixels and you have only one dark pixels. And assume the size of this image is 32 by 32. That means 32 lines we have, and in each line you have 32 picture elements, that is pixels. Then how will you transmit? 32 zeros. Assume 0 is for white pixel, or else in the reverse. 0 is for white pixel and 1 is for black pixel. It can be vice versa. Now, we have a continuous zeros and only one is there. So, in that case, this run length coding, how it is being used? For example, you assume then example binary stream. Assume that this is the thing I want to transmit. So, how will be transmitting? How many zeros are there? 6 zeros. So, 0, 6. And how many ones are there? 5 ones. Therefore, 1, 5. And then how many zeros are there? 0, 7. And how many ones in that case? 5. Therefore, 1, 5. So, in this way, this information will be transmitted. And still the engineers are very greedy and they want to reduce the compression ratio in a better way. So, always the first pixel is going to be an white pixel. Therefore, you need not to represent 0 itself. It can be further reduced 6, 5, 7, 5 and so on. So, what the first value indicates? It indicates our white pixel. 6 number of white pixels are there. 5 indicates 5 number of black pixels are there. Likewise, it is indicated. This is known as our run length coding. So, what is our next type of coding? Statistical coding. we will see the principle behind the statistical coding. The term statistics, what does it indicate? Statistical nature. So that means what are the statistical parameters we have? The very basic parameter of statistics is our probability. The probability takes a major role in the statistical encoding. So in the statistical encoding, we have two types. That is our static and dynamic. In the statistical encoding, we have a static and dynamic. Now we will see what is our statistical encoding. So the statistical encoding is based on the statistical characteristics of the information. Statistical characteristics of the information. So it is, for example, if here the characters, if I am assume it is for text compression, number of characters, probability of occurrence of each character, so these two are considered to do this statistical encoding. So what is an advantage of this? In our alphabets, the frequently occurred characters are our vowels. For these characters, we are going to assign a shorter code word. Shorter code word for frequently occurred characters. For rarely occurred symbols, for example, Q, X, Z. These are the examples, rarely occurred symbols. So for rarely occurred symbols or characters, lengthy code word can be assigned. So always the statistical, these are our characteristics, always this statistical encoding leads to one variable length coding. Variable length coding, because for frequently occurred characters, shorter code word. For rarely occurred characters, lengthy code word. In the conventional method, for each character, 7-bit ASCII code is used, whether it is rare or frequently occurred character. But here, based on the probability, we are going to assign it in a different way. So that is our statistical encoding. So under the statistical encoding, we have static and dynamic, right? What is the static encoding? Before you start the compression, before the compression process is started by the source encoder, the source encoder has the complete knowledge of the number of characters and probability occurrence of each character. For example, we are transmitting an image of transmitting a paragraph of content, and you are not going to do any edit in this paragraph, and you are going to transmit. By that time, the source encoder will do this analysis. How many times the character A has occurred? How many times the character B has occurred? Likewise, it will analyze the complete content and finds the number of characters and the probability of occurrence of each character. Then it is following the static encoding. That means static encoding has an complete knowledge of the characters before the encoding starters. Encoder has the complete knowledge of all the characters present in the text. all the characters present in the text. So vice versa, when you are considering dynamic encoding, the encoder doesn't have any knowledge about the number of characters and the probability of occurrence of each character. For example, when you are doing an voice chat chatting, online chatting, by the time we don't know what you will type as the next answer, what will be the next question. It is instantly being typed. So every time the encoder and decoder builds the tree to derive the code word. So in the dynamic coding, the encode doesn't have the complete knowledge about the characters. Then the static encoding also, we have the categories. Huffman coding, static Huffman coding. In the dynamic also, we have a Huffman coding. Then we have an arithmetic coding, and the third category is LZ coding. What is LZ coding? It is named after the scientist Lempel Ziv. LZ means Lempel Ziv encoding. In the dynamic, we have LZW coding, that is Lempel Ziv Wells coding. So in the static and dynamic Huffman coding, they are building the tree and then deriving the code word. Arithmetic coding here, for each string, one binary code word will be generated. Whereas for Huffman and this one, static and dynamic Huffman coding, for every character, the tree is built. In the LZ, Lempel-Ziv and Lempel-Ziv-Wells coding, these are the dictionary-based encoding algorithm. What is meant by dictionary-based encoding algorithm? The set of characters will be stored in a table and the index of that character will be transmitted while you want to transmit your data. It is based on the type of information and the specific property of information is being exploited by the compression algorithm. So, source encoding exploits the specific property of the information. So in the source coding, we have two categories. The first one is differential encoding. The source coding, we have a differential encoding and transform coding. We have a differential encoding. When this differential encoding is used, when the value of information, the dynamic range of the value of information is huge, but the difference between the adjacent values are very less, this differential encoding is used. And for example, the value is 10, 12, 35, 13, like. So, what is the maximum value? Assume that it is from 10 to 35. It is the range of the signal. But the difference between adjacent signal is assume like this. So, this 10 will be represented by 4 bits and the 12 can be represented by 4 bits. So, for every value, you are spending 4 bits of information. So, it is waste of bandwidth. So, in order to overcome this, the first value 10 will be taken and this difference only 2. What is its difference? 1, and its difference is 0 and so on. That means the difference between the adjacent values are less, than the dynamic range of our signal, 10 to 35. In that case, only this difference value will be encoded. That is known as a differential encoding. We will see the problem. And the next one is our transform coding. Before that, I will tell you this. Differential encoding, when the dynamic range of the signal is the value is high, the difference between adjacent values value is very less. Next, we are going to one transform coding. What this transform coding does? Converts one form of information into another form. It is not doing any conversion. It converts one form of information into another form which is more suitable. Which is more suitable to perform the compression. That is known as our transform encoding. So, in the transform encoding, this differential encoding and the transform encoding both are used in our image compression techniques. It is widely used. Transform coding, it converts one form of information into another form which is more suitable to perform the compression. I can explain this transform coding with respect to an image compression. We all know that the image is stored in the form of bits in the two-dimensional matrix format. So, assume that this is my matrix, this is my line 1 of an image, line 2 of an image, and these are the pixel elements. Totally 2 lines I have drawn and it has 6 pixel values. Assume that the first pixel value is, it is black, it is black, it is black, and these 3 are white, and again I have a black pixel. Whereas here the first pixel is a black, alternate pixels are black and white. In this case, if I plot the waveform for these pixel values, for line 1, the pixel amplitude I am taking in the y-axis is my pixel amplitude. It is a high value and it is a low value. So, the first 3 pixels are high and then the next 3 pixels are low and again high. When I am drawing it for my line 2, the first pixel and the second pixel. First pixel is high, second pixel is low. So, you will have the waveform like this. So, compared to this is my high frequency waveform and this is my low frequency waveform. The image compression exploits the limitation of our human eye. Our human eye is less sensitive to your high frequency component than to the low frequency component. Our human eye is less sensitive to the high frequency component than to the low frequency component. This we can explain with an example. See, now photograph of an image of the face, the eye is a more attractive portion because you have a white pixels and in between you have our eyeball and again white pixel. So, if you plot the waveform of an eye like this, you will get the waveform like this. whereas in the cheek portion you will have so many pigmentations. So because of this, the adjacent pixels will have a slight variation. So when you plot it as a waveform, it will have a high frequency. So when we are doing an compression, our eye is less sensitive to the high frequency information. So with the importance to this high frequency component can be made less. So it is not doing any compression. You have converted the pixel values into frequency coefficients, and it will be helpful to give less concentration or less importance to the high frequency components. So to do that, for the transform coding, there are so many methods are there. The first one is discrete Fourier transform, discrete cosine transform. Out of this DFT is more suitable for our, it's mostly used for our audio compression techniques, and DCT, that is a discrete cosine transform, is more suitable for our image compression, right? So with this, we have seen the compression tree of our multimedia compression technique. So in this, the lossless compression is used for our text, and these all are used. And here also, this differential encoding can be either lossy or lossless. The differential encoding can be either lossy or lossless. How we are saying it? When the difference is 10 and 12, when the difference is 2, I can represent, and I am using only 2 bits for representation, then this 2 can be represented by 1, 0, right? When the difference is 12 and 15, the difference is 3. Between 12 and 15, the difference is 3. But still I am using 2 bits for representation, and it can be represented by 1, 1. So there is no loss at all. So you can get back the values later. But when I have the values 20, when I have the values 20, the difference will be 5. 15 and 20, the difference value will be 5. So to represent this, I need minimum 3 bits, because what is the binary representation of 5? 101 is the binary representation of the 5. But because of this 2 bits representation we are using, this 5 will also be represented as 1. The maximum value will be used. So what is the loss here? 2 is a loss. So the differential encoding, when the number of bits used to represent the difference value is sufficient, it is giving our lossless. But when the number of bits we are assigning to represent the difference value is less, automatically we are missing the value, so that leads to lossy, right? So the differential encoding can be either lossless or lossy. So among this lossless compression is used for our text, and this is the tree for that. And in the lossy compression, this source encoding, that also comes under the lossless, and the differential encoding can be either lossy or lossless, and the transform coding, this is used for audio, and this is for image. There are so many transform coding techniques are there which supports our image compression.